Hey everyone. So in this video, we're going to talk about the circulatory system, continuing the conversation we started in the previous video, but now we're going to talk about the vessels. What I mean is the tubes that are going to be carrying the blood throughout your body. It's a fairly complex system and it begins with the heart, but we're going to talk about the heart specifically in a little bit. But you can think of the heart for now as just a pump. And what it is really two pumps. It's one pump that is pumping blood into your lungs, where that blood gets oxygenated and releases carbon dioxide. We talked about that last time. And then the blood travels to the other pump in your heart, and that pump, a stronger, bigger pump, is going to circulate the blood throughout your body. That's the pump that's going to push the blood throughout your body. What we're interested in this session is, what does that system look like that's delivering the blood? We'll get to the heart, but what does the system look like that's delivering the blood? What do the tubes look like? Basically, it's going to be made up of arteries, arterioles, capillaries, venules, and veins. And I'm going to talk about each one of those separately. But you should know that this system is also fairly complex because it involves all parts of your body. We're going to simplify it, but just so you can appreciate how extensive it is. If you took out all the capillaries, all the veins, all the arteries in your body, and you lined them up like one long string of all these tubes, from the tiniest little tube to the biggest tubes all together, guess how long it would be. Now, I can't hear you guessing, but I think you're guessing like a mile, 2 miles, 3 miles, 60,000 miles of tubes. If I just opened you up and could take out all the microscopic tubes to the big tubes and line them all up, I could wrap it around the earth about 3 or 4 times. That's insane, right? So that's an extremely complex and entwined system. We want to wrap our heads around it a little bit. So to begin with, we're going to begin with the arteries. But really, let's begin, to keep it kind of simple, with the heart. So, super simple. There's a heart. So you can see it. Now, one thing you're going to notice in this class is I'm no artist. Fine. There's our heart. Things start with the heart. And we have tubes that are coming out of the heart. The one that comes directly out of the heart is called the aorta. And this is an artery. So by definition, any tube that is coming and delivering blood from the heart, coming out of the heart and delivering blood, is called an artery. And the ones that are returning blood back to the heart, those are the veins. So arteries deliver blood, veins return the blood. The aorta is a big tube, like, I don't know, the size of my thumb maybe, 2/3, 3/4 of an inch across, something like that. Depends on the size of the person, maybe 1/2 inch across in a smaller person. And that's going to be a pretty robust tube. It's going to have some smooth muscle around it. And here I have to stop for a second. What do I mean by smooth muscle? Well, in your body, broadly speaking, there's 3 kinds of muscle. There's skeletal muscle. You know about that. Biceps, triceps, go to the gym, dude, build up the tris. Those are called skeletal muscles. That's a particular kind of muscle. It has different characteristics too, depending on which muscle it is, but basically it's a type of tissue. Then there's myocardial muscle. Myocardium just means myo, meaning muscle, and cardio, meaning heart. The heart is a big muscle, or it has big muscle tissues as part of it anyways. And that is a specific kind of muscle. We'll talk about why later, but it's special and distinct from other muscles in your body. And then the other muscles are smooth muscles. And smooth muscles are the muscles that you don't control and you don't go to the gym to work out. They're the muscles that are like around your intestines and squeeze your intestine in a particular order to push digested food out and allow you to poop. Or other muscles that you don't control. So there's a lot of muscles in your body that are moving things, that are shifting things, etc. You don't control those. Those are called smooth muscles. And around your arteries is a significant amount of smooth muscle. Muscle that can move and open and close the size of the hose, of your arteries. And when we talk about the inside size of the hose, we talk about the lumen. So the lumen is the inside part that transports blood. That passageway is called the lumen. So by dilating and constricting, getting bigger dilation, getting smaller constriction, your arteries and your arterioles can allow in more or less blood into the rest of your body. So we begin with the aorta, but really from the heart, what we get is passageways that are relatively robust because they've got muscle tissue around them, and those are called arteries. And then they break up into smaller but still robust tissue, or hoses I should say, and those are arterioles. So the artery might be half an inch around. The arterioles are going to be smaller than that. They're going to be the branching part that breaks off. The arteries tend to be more flexible. And you can imagine why, right? Why would arteries be more flexible? Because the heart's pumping. It's going like ba-boom, ba-boom, ba-boom. You're not aware of it, but your arteries sure are. They're getting like this flush pressure every time your heart beats. And they need to be able to adapt to that. So they have in them flexible, elastic fibers that allow them to accommodate that change in pressure. As we go further down the system to the arterioles, we have less of that flexible capacity. But early on, it's going to be really flexible. And then later on, in the arterioles, we'll have less flexibility, but we're probably going to have more smooth muscle response. In other words, the arterioles are going to dilate and contract more significantly. They are really the place that's going to control how big of a passageway we're allowing for blood. So if you'd like to think of it this way, you could see the arterial or the arteries are distributing the blood through the major passageways, the highways, and then the arterioles are providing restriction or access to allow a control for flow. The arteries' flexibility actually helps with the pumping. Then you can imagine why. The heart's going boom, 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 but you don't want blood to flow through your body going. So expanding and contracting allows it to absorb some of that flush, and then by contracting back, by squeezing back with that flexibility, the arteries keep the blood moving relatively evenly. Okay, so there's the arteries and arterioles. A reasonable question at this point would be, why do we need this capacity? Why do we need to be able to dilate our vessels or constrict our vessels? That's a good question, because we're trying to preserve homeostasis. In the last video, I told you that your body likes a specific pH. It also likes a specific temperature. And let me use that as an example of a case where we might want to control the size of our vessels and the flow of blood to parts of our body. Your body likes to be at about 98 degrees, right? Let's say you go out and it's really hot. Well, now your body senses this heat, and so you start sweating. This is a response. And the sweat evaporates, and that helps you dispel some of your heat, dissipate some of your heat, so that your body doesn't get too hot. What makes that more effective is that your arterioles are going to dilate. They're going to open up, allowing more blood to flow out to your arms and to your feet. And your arms and your legs are going to operate as radiators. We're going to have blood flowing through them. You're going to be expending heat to the environment so that your core doesn't get too hot. Your body's really interested in making sure your core stays at 98 degrees. And so it's going to open up the vessels to allow more blood flow, to allow a cooling effect. More blood goes along the surface of your body, and as the blood is exposed to the surface of your body, it can dissipate some of that heat that's being generated. Where's the heat coming from? We talked about it last class session, right? Last video. The heat is coming from you generate energy. You're oxidizing sugars, and that generates energy. Some of that energy is heat, and you need to let that energy go when it's too hot out, because you want to maintain homeostasis, and that requires about 98 degrees Fahrenheit. Okay. already, this should make some sense, because at some point you went into, I don't know, a hot tub or a sauna or something like that, and you got all red. You've probably noticed this. You sit in a sauna and your face gets all red, your hands get all red. Your body is sending blood to your extremities to try to keep it cool as it's faced with this stress of excess heat and possibly allowing the core to get too hot. What if you go out and it's really cold? The opposite happens. The arterioles constrict, allowing less blood to flow. And you might say, well, I want more blood to flow because I want my hands to stay warm. You don't want your hands to stay warm at the expense of your core. Your body is concerned with maintaining your core temperature. So it's going to constrict flow to your hands and to your feet in order to keep that warm blood more in your core so that your core doesn't get too cold. If it allowed all that blood to flow out to your extremities, the blood would come back colder and it would cool down your core. That's not going to be good because we want to maintain homeostasis. So we slow down circulation. And you know this because at some point you've been out and it's cold and your fingers get really cold or like white. This is your body accommodating the cold by slowing down circulation. And it does that by constricting the arterioles to reduce circulation to your extremities. There's other ways this might be helpful too. Let's say an injury. You cut off your finger. You're going to bleed, right? Your body's going to send more blood. It's going to dilate that vessel as an automatic response to an injury to send more fluid to wash out that injury and, much more importantly, to send defensive mechanisms to protect you against infection. So your body's going to recognize we've been injured. There's a possibility of infection, and I need to send specialized cells that are going to help fight that infection. And to do that, your arterioles are going to dilate, allowing more flow in. There'll also be some other effects that allow clotting, etc. We'll talk about that later. But for now, know that you're going to get dilation as a result. And not just dilation, but what we'll talk about later is filtration. That is to say, the walls of your vessels are going to open up a little and allow more fluid to escape out so that some of those particles that could help with the healing process are going to be able to get out of your vessels and get into your tissue and fight the infection and help the healing process and help clotting and other things like that. We'll talk more about that later. Okay, so far, our blood has gone through arteries, gone through arterioles. The arteries are flexible but firm. The arterioles are firm and the key part of dilation and constriction. From there, it goes into a bunch of very, very, very small vessels called capillaries. So I don't know how to draw this, but tons and tons and tons of microscopic vessels. Little tubes that are too tiny to see with the naked eye. In fact, difficult to see under a microscope. Lots of them. This is basically where the tens of millions of miles of vessels comes from. It's mostly capillaries. Because if you think about it, like every muscle tissue, every organ is just completely filled with all kinds of capillaries because it has to be. These are the tiny little vessels that are bringing blood and therefore bringing oxygen, bringing nutrients, and taking away carbon dioxide to all parts of your body. So these capillaries, as you can see there, are so small that red blood cells in the smallest ones have to pass through one cell at a time. They're literally going single file through the capillaries. And the wall of the capillaries are like one cell. You see that capillary there? That capillary is showing you one cell that's sort of half curved around, creating a wall. So the walls are very thin and the capillaries themselves are very, very, very microscopic, right? This is where we get the 60,000 miles of vessels traveling through your body. And that sort of, at this point, should make sense for you. All one cell thick. Why are they so thin? Because oxygen and carbon dioxide have to be able to go through them. You've got these red blood cells going through one cell at a time. They have the job of delivering oxygen and absorbing carbon dioxide. For that to work, the oxygen and the carbon dioxide have to be able to go through the walls of the capillary. And they do. And they exchange, therefore, gases with the surrounding tissue, providing oxygen and absorbing carbon dioxide. one cell passing through at a time. Some of the capillaries are a little bigger, some of the capillaries are a little smaller. Well, the smallest they're going to get is going to allow one red blood cell through. Nothing's going to be so small that at least one cell can't get through. So those are the capillaries. Typically, we talk about capillary beds, which is just basically the tissue that's got all those capillaries in it that's allowing that exchange of nutrients and gases. In addition, as I mentioned before, there's going to be some capacity in these capillaries for other bigger products to actually go through. Maybe some red blood cells, certainly some smaller particles, certainly some defensive particles that we'll get to later, some defensive cells. So there's going to be what we call slit pores, but holes, gaps in the wall that are just big enough for smaller particles to get through, and maybe every now and then a larger particle like a protein, which is a pretty large particle, to get through. And what's the point of that? Well, those are going to go into the surrounding tissue and defend us against infection and other kinds of issues. So this is all good. We'll talk about that in greater detail later. So once it's gone through this intense capillary bed, all this tissue here, which is, throughout our body, it's going to have to be recollected. And it's going to be recollected in hoses that are kind of soft, too small to have soft or smooth muscle around them. And those are venules. The capillaries themselves, for those of you that are more science-minded, are probably about like 5 to 8, maybe 10 microns. The venules, probably 10 to 30 microns. So if you're excited about that, fine. If not, know that the capillaries are very, very tiny. The venules are bigger because they're collecting back all the blood products and bringing them back in to larger vessels. But still, not vessels that are going to have smooth muscle in them. So remember we talked about the arteries and the arterioles and how those dilate and contract. These don't. These are bigger, but they're soft and floppy. That's sort of going to collect all the blood, and then it's going to bring it back to veins. The veins, as you can see from the image I'm showing you, are bigger than actually the arteries, but under less pressure. And the reason for that is that there's very little pressure left. I mean, the heart pumped blood. It went through the arteries, through the arterioles, through the capillary beds, and now it's sort of spent in terms of pressure. And so the veins are pretty big to allow the collection of that blood, to allow it to keep moving, with some smooth muscle around them, but not much smooth muscle there. So they are not going crazy in terms of controlling volume the way the arterioles are. And if you look at that image, you can see that the arteries, much more defined, much more structured, with a lot of smooth muscle around it. That's what that pinkish layer is. And the veins don't have as much smooth muscle around them and aren't nearly as defined and are kind of floppy, right? This is why sometimes if you've ever had like an injection or an IV, intravenous line put into your arm, sometimes the nurse will have trouble putting that in because your veins are kind of floppy and getting something in there can be a little tricky. Okay, so the point of the veins is to bring the blood back through the circulatory system so that it can get back to the heart and begin the whole process over again. So these are flexible, open lumen, softer tissue kinds of veins without very much pressure in them at all. In fact, they have so little pressure in them that if we just relied on what we call hydrostatic pressure, that is just the absolute pressure in blood to bring it back to your heart, it won't get anywhere near your heart. In fact, the blood down in your feet, if you're standing up, probably only has enough pressure left in it to get up to like halfway up your calves. So it's not pressure that's going to push it up to your heart. Now, we could just have more pressure, right? Why didn't we evolve with a much bigger, powerful heart that provided enough pressure to have the blood circulate all the way through without disruption? Well, because then we'd have a lot of pressure in that capillary bed, and that would tear apart the capillary bed or allow a lot more blood products to travel through the tissue, etc. We don't need that kind of pressure. That's going to be damaging. That's going to damage the arteries. In fact, high blood pressure is a problem. We'll talk about it in the next video. So we don't want high pressure. We want the pressure we've got. But the question becomes then, how the hell does the blood get back to the heart? How does the blood that goes down to your feet and is now fighting gravity get back to your heart after going through tubes that are microscopic in size? And the answer is, in my view, kind of super cool because the veins create their own pumping action. You see, in the veins, there are these valves, and these valves kind of stop the blood from flowing in one direction and allow it to flow in the other direction. So, put simply, those valves look something like this. Here's a vein going up from your legs. And right here, we have endothelial lining, which is just a fancy word. I'm going to draw this, and it's not going to be awesome, for the inside lining of your veins. Endo meaning inside. So we have these folds, which is what I'm trying to draw and not doing an awesome job of it, but you get the idea, maybe. These folds that will allow blood to flow that way, flow up, but it won't allow blood to flow down, because if the blood flows down, it's going to kind of function like a valve. The blood flows up, and then it closes, and the blood can't push down on the valve, as you can see from the image that I've got up there, as well as my fantastically drawn image. Okay, so far what we have is then these kind of compartments in the valves where blood can only move in one direction. That's not a pump, but maybe it's the starting point of a pump, right? Well, one thing to realize is that these veins travel in what we call bundles. So basically, arteries, veins, nerves, typically are going to all travel together in a bundle. That's already helpful because those arteries are pumping. And I told you before, they're flexible. So they're moving in and out. That action is going to squeeze the veins. And if you squeeze that compartment that I drew, it's going to push the blood up, and the blood can't go back down. More than that, you move. So every time you move your legs, etc., you're squeezing muscle. You're squeezing veins. Squeezing, releasing, squeezing, releasing. So people say movement's great, walking's great, etc. It is great. It's great for muscular development. It's great for tone. It's great for bone health. But it's also great for vascular return because you're squeezing the veins and pushing it back up, back toward the heart. We call this passive constriction. So we're basically not relying on the veins themselves to move the blood back, but the surrounding muscles and arteries and general movement to squeeze and release, squeeze and release, squeeze and release, and that pushes the blood back up toward the heart. There's one more function that's going to be key here, and that is the change in pressure in your body, in particular in what we call the thoracic cavity. The thoracic cavity is just this part of your body, like where your lungs and your heart are. That's the thoracic cavity. When you breathe in and out, that changes the pressure in your thoracic cavity, which is kind of obvious, because if I expand my chest, I breathe in. Why? Because I reduce the pressure in my lungs, which sucks air in. And then when I breathe out, my diaphragm and my chest muscles push my lungs together, and that creates higher pressure that pushes the air out toward the relatively lower pressure outside. But it does something else too. It squeezes against my venous system. And in particular, in the middle of your body right here, to collect all the blood coming in from your veins, there's something called the vena cava. And we talk about a superior and inferior vena cava. That doesn't mean one's better than the other, but in medicine, superior means it's higher up, inferior means it's lower down. So we have basically two large compartment-like veins, and they are collecting the blood as it works its way up the veins from all the parts of your body through those valves. By the way, if you wanted to see the valves, check out your own body. I don't know, if I looked at my arm here and I maybe blocked off flow and did a little bit of this. Oh, can I even? There you go. Okay. Can you see that vein bulging? And can you see how right in the middle there is that bump right there? Let me show you again. That bump is a valve. It's just a fold, like I've described, that gets the blood to only flow in one direction. So every time I move my hand, I'm allowing the blood to work its way back toward the vena cava and therefore toward the heart. What does vena cava mean? Well, cava is just Latin for a compartment with a lot of entryways into it, which is where we get the word cave, because that's what a cave is, right? It's like a big hole with a lot of entryways to it. Vena means Venus, right? So vena cava. Inferior, superior. The superior takes the blood from your head. The inferior takes the blood from your lower body. It brings it up, collects it, and then makes it available to your heart. Your heart sucks it up and starts the whole circulation process all over again. Already, this should tell you something, like movement is good because movement causes blood circulation. Massages aren't a bad thing either. That's why massages feel so good. And you know, when you have a massage, if you ever have, and I have not, because honestly I find them a little bit creepy. I don't really want a stranger rubbing my body. But if you like massages, you know that the massage therapist is always going to kind of push up, push toward the heart. Why? Because they've been trained to do that, because what they're doing is they're promoting vascular return. They're promoting the movement of blood back up through your system. And when we talk about circulatory pathologies with the next, a video in a couple of sections later, we're going to talk about when that doesn't quite work out. But for now, this works out pretty well. Let me propose an exercise that you can do right now while watching this video. What I'd like you to do is take a really deep breath and hold it. Just keep holding it. And now if you have a mirror, go ahead and find yourself a mirror. I'll wait. Okay, got your mirror? Cool. Okay, now look at your face. Keep holding your breath. Your face is getting red. Why is it getting red? Because the blood can't get back. Remember I told you, breathing expands and contracts your vena cava, which helps draw blood in. When your vena cava opens up, it draws the blood in from your venous system. So as you breathe, you're also drawing blood back into that central compartment that makes it available to the heart. Cool, right? So right now, your face is probably beet red because you are keeping a high pressure in your thoracic cavity. And that means your vena cava is not expanding, and that means your blood can't get back in. But your arteries are still delivering blood. So your arteries are delivering blood to your head, and it has nowhere to go, so it's building up in your head. And at this point, your head is bright red. Awesome. Science is awesome. In addition to that, check out your jugular veins. Your jugular veins are really bulging out. In medicine, we call that jugular vein distension, or JVD. Why? Because they're filled with blood. These are veins trying to get blood back into your system, and it can't because you're maintaining a high pressure against your vena cava, so the blood can't work its way back. Okay, go ahead and breathe. It was all worth it for science. Now, those of you who are still conscious have learned an important lesson. Those of you who are unconscious have learned an even more important lesson, which is don't always take my advice literally. Okay, so this is why, for example, when you yell and scream and maintain a high thoracic pressure, your face turns red. Or if you ever watch an opera singer and they're holding a note for a long time, their face gets red. The blood can't work its way back in because you're not getting that draw back into the vena cava. In addition to that, a couple of interesting notes. That circulatory system, which I already mentioned, includes your bones. So there are veins and arteries that go into the central part of your bone. I know you think about bones as though they're just like inert structures. They aren't. They are living tissue. So in the middle of the bone is actually bone marrow, active biological bone marrow in something called spongy bone. Spongy bone is kind of misleading. It's not soft like sponge. It is more flexible than the outer compact bone, the hard bone, but it's not really spongy. It's more like, a hard sponge-looking thing. But it creates a lot of compartments where there's a lot of bone marrow. And that bone marrow is doing things like creating red blood cells. Red blood cells are made in the bone marrow. That's where they're generated. And other kinds of defensive cells. Cells that we'll talk about later, B cells and T cells. Well, B cells anyways, are made in the bone marrow. So there's aggressive circulation through the bone as well. So much so that in medicine, in emergency medicine, we do this interesting thing. We always want access to somebody's circulatory system, right? Like if somebody is having a heart attack or any kind of respiratory emergency or whatever, one of the first things we want to do is put in an IV to provide some access. So if we need to give them medication or fluids or whatever, we can do it. But that's not easy to do because, as we've talked about, veins a lot of times are pretty floppy. And if somebody, for example, has lost some blood, those veins are even floppier, so getting an IV in there can be really tough. So we actually sometimes use IO drills for IO access, interosseous access. We drill a hole with a little hand drill. It's a tiny little drill. It's not as scary as you think. Right into the bone and put in a catheter, put in a metal tube that's basically going to allow us to inject blood or fluid or other things right into the bone. And the nice thing about that is the bone is solid, so even if you're in crisis and all your veins are collapsing, we can very quickly put a little hole right into your bone and provide you with the fluids or the medications you need to save your life. So this is actually an increasingly popular way of providing IV access, in this case IO access, in an emergency. And it just shows that actually the bones are an active part of your circulatory system and producing red blood cells, etc. Now, as you grow older, the activity of inside those bones slows down. So if you are 12 years old, your bones are very, very active. Your age, your bones are pretty active. My age, probably just my flat bones. So things like my chest, my pelvis, maybe my scapula, those are still active and producing defensive cells and doing things. But a lot of my long bones, my femur, my funny bone, my bones that define my legs, etc., those are probably filled with sort of like a yellow marrow, which is more fatty and not as biologically active anymore. However, having said that, if for some reason I needed more blood cells, they could be recruited to actually start generating more red blood cells. So your bones, again, part of your circulatory system. In addition to that, it's worth pointing out that your circulatory system has other interesting dynamics to it. So for example, it's the thing that provides nutrition, or I should say, absorbs nutrition from your intestines and moves it to your liver in order to provide nutrition and important minerals and other things for the rest of your body. So we call that the portal vein. So the portal vein basically just connects your GI system, in particular your intestines, to your spleen and your liver and other things we'll talk about in order to allow for the delivery of nutrients. And then there's some other variations that are kind of cool. Like, for example, around your brain. Your brain is super sensitive. So remember I talked before about how your whole body wants to maintain homeostasis, so it wants a certain pH, it wants a certain temperature, etc. Your brain is even more sensitive than that. So it has a protective membrane. Literally, blood can't just go to your brain. It goes through a semi-permeable membrane, what we call the blood-brain barrier, that makes sure that certain particles can't get to your brain. And in this way, it protects your brain and your central nervous system from infection. This is a good thing. It's very protective. I mean, evolution did a good job here. Having said that, can you see how it could also be a little bit problematic if you're a doctor? If somebody does have an infection, it's a little bit harder to treat. Making drugs and pharmaceuticals that can get through that blood-brain barrier and treat a problem in the central nervous system is pretty tricky. So it creates a challenge in medicine, but in evolutionary terms, it's fantastic because it's protecting your brain against possible infections. And if you did get an infection in your brain or central nervous system, that's a super huge bad deal. So it makes sense that your body wants to protect you against that. Okay, so that's what we're talking about in this video. We're done for now. We're going to, I think, pick it up with a short video that's going to talk a little about blood pressure and measuring perfusion. And that'll be it for this section. And then we'll go on to the next section that's going to talk about some pathologies, some dysfunctions with the systems we just talked about. I'll see you then.